Hello. So now we will proceed with the general process, general thermodynamical process, for which the equation we have taken as PV to the power n is equals to constant. So what we will do, we will derive the values for work done, heat given, and the change in internal energy for this general process. And whenever any question will be given to us, we'll compare that process with the general process and we will get the value of n. And by getting the value of n, we'll put this value into the predefined formulas, which we have already memorized. Okay, so here we'll get those formulas first. So PV to the power n is a constant. This is a general process we have defined. The n can be any real number. Okay, so the first thing we want to calculate with this process is the work done by gas. Work done. So for a closed process, we have a formula for work done by the gas, which is P dV. This is a differential formula. So in this formula, there is P and there is VB, and I cannot integrate directly because both P and V are variables here. So what I will do, I'll replace the value of P from the general process. So dWg will be equals to K times of dV upon V to the power n, where K is a constant. This constant I am defining as K. Okay. So let's integrate this formula. If I integrate this differential equation, dWg, K is a constant, so I am taking it out, dV V to the power n. I am integrating this equation from V1 to V2, or we can go for the indefinite integration. So the integration will become Wg is equals to K times 1 minus n 1 upon V to the power n minus 1. We'll put the limits from V1 to V2. Okay, let's put the values. K upon 1 minus n 1 upon V to the power n minus 1 minus 1 upon V1 to the power n minus 1. Okay, let's multiply this K inside. So our Wg will become 1 upon 1 minus n K V to the power n minus 1 minus K times of V1 to the power n minus 1. This is our equation 1. So this V1 and V2 are the values of volume at state 1 and state 2. And obviously this state 1 and state 2 will satisfy this equation also. So let's put those values in this equation. So we'll have P1 V1 to the power n is equals to P2 V2 to the power n and is equals to K. So I'm having the value of K from this, and I can replace this value, I can put this value into this equation. So from equation 1, I'll have Wg is equals to 1 upon 1 minus n. Here you see this K upon V to the power n minus 1. What I'll do, at this point, the value of K, I'll put this one. So it will be P2 V to the power n divided by V to the power n minus 1. Minus, and this value of K, I'll replace the P1 V1. So P1 V1 to the power n divided by V1 to the power n minus 1. Upon simplification, we'll have 1 minus n P2 V2 minus P1 V1. This is your Wg. This is the work done by the gas for this general process. But if you remember, we want to have the equation in terms of temperature, we like those. So what I will do, I'll use the ideal gas equation. So from ideal gas equation, so ideal gas equation will also satisfy the state 1 and state 2. So from ideal gas equation, we can have P1 V1 is equals to nR T1 as well as P2 V2 is equals to nR T2. If I replace the value of P2 V2 and P1 V1 into this, we'll have equation Wg is equals to nR, I'll be taking common, divided by 1 minus n T2 minus T1. So this is the equation for the work done by gas in terms of temperature. Okay. So if I convert this equation in differential format, this equation will become dWg is equals to n times of R 1 minus n dt. So this equation is the equation for work done by the gas in terms of temperature for this general process. Okay. So this is the equation. If you want, we can memorize this equation. This n is the number of mole. Let's take this n as capital N for a time being. So I'm taking it capital N. A capital N represents the number of moles here. Okay. Okay, now let's go for the calculation. This is the work done. Now let's go for the internal energy. So if you go for internal energy, we have a formula for that. Because we know the internal energy does not depend upon process, whether you are going for any specific process like isochoric, isobaric, or you go for general process. The differential equation for internal energy is NCV dt. This is the differential equation for internal energy. This is the differential equation for work done by gas. This is the differential equation for internal energy. And if we go by the first law of thermodynamics which have dq is du plus dwg. Let's put the values. So we'll have dq is equals to ncv, capital N CV, because the number of moles I'm defining as capital N, CV dt plus capital N R upon 1 minus n dt, which will become capital N CV plus R upon 1 minus n dt. This becomes the equation for heat in terms of temperature for our general process. Now if we go for 1 mole, the capital N value will become 1. So this equation will get converted into, and let's put the value of CV also. If we put the value of CV and if we take R common, we'll have R times of F by 2 plus 1 upon 1 minus n times of dt. And if we want our formula in terms of gamma, I can rewrite this equation as R times of 1 upon gamma minus 1 plus 1 upon 1 minus n times of dt. Any one of the equation you can use. Either you can use this one, or you can use this one, or you can use this one. Okay. So let's summarize this. So we started with general process. Reason being we cannot cover all the process. If you go for thermodynamics, there can be any number of processes which are possible. So we have already studied some specific process: isobaric, isochoric, isothermal, and adiabatic. So if those are the processes, we have the formulas. What if the general process, if the examiner will provide you any process which is different than those 4 processes? So if we don't have any ready-made solution for that, we do have to do all these calculations in the question itself, which is very time consuming. So to save that time, what we do, we start with a general process, which is PV to the power n. And we know how to convert the process given in the question into this process and how to get the value of n. Okay, so for this process, we will be calculating everything. So we have started with this process, general process, where n is any real number. And for this process, we started calculating the work done. When we started calculating the work done, we got this formula by putting the values there. And this formula, in this formula, there was this k which was constant, and n was this number. And we want the formula, if you remember, we want the formula in terms of temperature, because temperature is like unique, something unique, which is a state function. So we converted this formula in terms of temperature. This formula gets converted to this formula, and then after using the ideal gas equation, we got this formula in differential format. We got the work done by gas in differential format, which was equals to R upon 1 minus n dt for 1 mole. Capital N was the number of mole. Obviously, if you are having the more number of moles, the work done is a scalar thing, you can just multiply it. So After getting the work done by gas for the general process, we went for calculating internal energy. And change in internal energy is independent of the process. We already know that. We directly utilizing that. We started utilizing that formula. Then we went for first law of thermodynamics because we want to calculate how much heat, meaning what kind of change is happening corresponding to the heat given to the system. So we got the formula, differential formula for heat given in the system in terms of temperature, and then we modified that formula for 1 mole. So for 1 mole, it came out to be R times of F by 2 plus 1 upon 1 minus N times of dt. Here this F by 2 depends upon degree of freedom. It depends upon the gas. This is the quantity which depends upon the gas, what kind of gas you are using, whether it is monatomic, diatomic or polyatomic. And this is the quantity which depends upon the process, what kind of process you are following. So both the things are coming here. If you change the process, the heat required to change the temperature will change. If you change the gas, heat required for change to change the temperature will also change. So we got the ready-made formulas now for general process to calculate work done, to calculate internal energy, as well as to calculate the heat. Okay. Thank you.